name is David Schmoll from the University of Vienna, and today I would like to give you a short research update on two of our newest publications about yeast GGG samples at cryogenic temperatures. You may rightfully ask why we care to go to cryogenic temperatures. After all, experiments are easier and cheaper to conduct at room temperature. The motivation behind this step is connected to a comparably new research direction in Magnonics, interested in the quanta of spin waves, also called magnons, and the corresponding physics at very small energy scales. This area of research requires long coherence times, which is why we need to exclude the interaction of the investigated coherent magnon states with thermally excited spin waves. As magnons follow Bose-Einstein statistics, the concentration of thermally excited magnons decreases exponentially below 100 millikelvin, which is why low temperature environments are needed in quantum magnonics.
To cover a continuous temperature range from room temperature down to millikelvin temperatures, we use two experimental setups. Here we are standing next to the first setup, a physical property measurement system or PPMS, which enables spin wave investigation from 400 Kelvin down to 1.8 Kelvin. With different measurement tools, like for example this stick here, we're able to perform FMR measurements, propagating spin wave spectroscopy and VSM measurements. Our second experimental setup, a dilution refrigerator system, enables us to perform FMR as well as propagating spin wave spectroscopy studies in a temperature range from 4 Kelvin to 10 millikelvin. Next to me you can see an open dilution refrigerator with the different thermal stages from 50 Kelvin at the top to 4 Kelvin, 1 Kelvin, 100 millikelvin, and finally the mixing chamber stage, which is cooled down to base temperature of 10 millikelvin. Our sample is mounted in a sample holder, thermally connected to the mixing chamber stage, therefore also cooled down to 10 millikelvin. We glue our yeast stripe onto an antenna PCB with two antennas, which is electrically connected to the transmission lines of the dilution refrigerator operating from PC to RF frequencies. The transmission lines are then connected to a VNA placed outside of the dilution refrigerator.
Our current research is concerning which material should be used to host magnonic quantum states. In our opinion, yttrium iron garnet, or YIG, would be the material of choice, as it is well established in the research community, offers long magnon lifetimes, a high spin density which promises strong coupling to other quantum systems, and YIG structures are scalable to the nanoscale with state-of-the-art nanofabrication techniques. However, the drawback is that high-quality YIG films are usually grown on gadolinium-gallium garnet substrates, or GGG. It is well known that GGG shows paramagnetic behavior at temperatures below 200 Kelvin, leading to a magnetic stray field oriented antiparallel to the external bias field in the in-plane magnetized configuration. This stray field is highly inhomogeneous and leads to a shift of the spin wave frequency and to different resonance conditions along the sample film, resulting in asymmetric peaks at decreasing temperatures and increased line widths. My colleague Rostislav has demonstrated how to calculate the stray field independence of temperature and the applied external magnetic field in his two recent articles.
In our recent article, published with open access in the journal Low Temperature Physics, we were able to provide direct evidence for the inhomogeneity of the GGG substrate stray field and showed how to eliminate the correlated line width broadening.
We performed FMR studies in the PPMS at temperatures between 300 Kelvin and 2 Kelvin with three different samples: a plain 150 nanometer thick YIG film grown on GGG, a patterned 500 micrometer wide stripe on GGG, and a patterned 500 x 500 micrometer square on GGG. Measurements were then conducted in four configurations, with the plain film and the stripe positioned parallel to the bias field, and with the square and the stripe positioned orthogonal to the external field. In the first two configurations, the YIG film is exposed to the inhomogeneous area of the stray field, while in the other two configurations, the YIG film is only exposed to the homogeneous field area. Comparison of the FMR spectra at 300 Kelvin and 2 Kelvin manifests that the asymmetric broadening of the FMR signal is due to the inhomogeneity of the GGG field. The results presented until now concerned FMR studies without propagating spin waves. However, we believe the switch from standing waves to propagating magnons is crucial for quantum magnonics, as it enables the transport of information between a separated source and a detector. This objective motivated the investigation of the wave number dependence of magnon dissipation in the case of propagating spin waves. It resulted in our recent article published with open access in Physical Review B. We recorded spin wave transmission between two antennas separated by 4 mm in a 7.8 micrometer thick YIG film grown on GGG and compared the S21 parameters for various temperatures between room temperature and 26 millikelvin. The sample was placed in a dilution refrigerator between a heavily attenuated input transmission line and an output line equipped with an amplifier. The external magnetic field was adjusted at each temperature to overlap the spectra in the frequency domain at the room temperature FMR frequency. The highest transmission was observed at room temperature, the lowest transmission at 4 Kelvin due to the increased losses by rare earth ion impurities, and an again increased transmission at millikelvin temperatures, where the contribution of the impurities is not dominant anymore. To compare the magnon transmission and losses with wave number, we need to transform the obtained spectra from the frequency domain to the K domain via the dispersion relation. The dispersion was calculated analytically for a two-layered magnetic structure, considering dipolar coupling, and compared to micromagnetic simulations, showing good agreement of the results. The analytical model is represented by the solid lines and the numerical model by the color map. Both methods allow also to directly calculate the dissipation rate as the imaginary part of the frequency. Detailed information regarding both dispersion models can be found in the full article. The transformation of the spin wave spectra to K-space immediately reveals the wave number dependent magnetic losses at the different temperatures. While we can excite all accessible wave numbers at room temperature, we can excite only approximately 1/3 of the possible wave numbers at 4 Kelvin and about half of the accessible K at millikelvin temperatures. Additionally, we observe practically no changes of the transmission signal below 500 millikelvin, which we attribute to the complex and highly frustrated magnetic structure of GGG below 500 millikelvin, already known from literature. From the transmission spectra, we can now directly calculate the dissipation rate at the respective temperatures via the S21 parameters, the antenna spacing, the antenna efficiency, and the group velocity as the derivative of the dispersion relation. We can take a look at the dissipation rate at a fixed wave number versus temperature and replicate the behavior observed in the transmission spectra in frequency space. Lowest dissipation at room temperature, highest dissipation at 4 Kelvin, and a decrease of the dissipation rate down to 500 millikelvin, from where we see no further changes. As a further step, the dissipation rate was calculated for all recorded wave numbers, revealing an increase of the dissipation rate with K in the experimental wave number range. This behavior is attributed to the dipolar coupling of the YIG and GGG layer, which opens an additional dissipation channel to the GGG substrate for propagating waves. As mentioned before, the dissipation rate can also be extracted from the analytical model, shown by the dashed lines. We observe good agreement between model and experiment down to 1 Kelvin. At lower temperatures, the model overestimates the damping as it considers a temperature-independent GGG linewidth and does not consider the stagnating GGG magnetization below 500 millikelvin. In the model, we can also calculate the dissipation rate for higher wave numbers than in the experiment, which interestingly predicts a dramatic shrinking of the dissipation at higher K, as the dipolar coupling decreases exponentially. The theoretical predictions suggest higher wave number magnons as possible candidates for future experiments on the quantum level in YIG. In conclusion, we can summarize our articles in two parts. In our first article, we were able to provide direct experimental evidence of the inhomogeneous GGG stray field as the origin of the observed asymmetric broadening of the FMR linewidth. Furthermore, we report that microstructuring of the YIG film allows to successfully avoid the parasitic broadening and significantly decreases the linewidth to temperatures down to 10 Kelvin. In our second article, we provided clear experimental evidence that the dipolar coupling of the YIG film and the magnetized GGG substrate at cryogenic temperatures leads to a wavenumber-dependent dissipation rate. After an initial increase of the dissipation at low K, the theoretical model predicts a dramatic decrease of the dissipation rate at high wave numbers, as the dipolar coupling between the two layers decreases exponentially. Hence, short wavelength exchange-dominated magnons could serve as promising candidates for quantum magnonics in YIG-GGG platforms.